Yeah, thanks to the organizers for inviting me and giving the opportunity to talk, also to the organizers of the program. It's a pleasure to be at IIS for a whole month and get away from my duties at Hamburg. I can tell people, no, sorry, I'm far away. So I want to change the topic slightly. It will not just be about real structures. I want to talk about the topology and real structures in toric degenerations. So embarrassingly, Mark and I have promised a topology paper for, I don't know, maybe 15 years or so. And it just is never coming out, but that's a bit of a replacement. So obviously, I'll use a lot of my discussions with Mark over the many years, and then I'll specifically report on work with Julia Argus. That's on the real structures in Kato-Nakayama spaces. With Helge Rudert on period integrals and trapezoid cycles, and on work with Mark, Paul, Hacking, and Sean Keel on K3, and on theta functions. So I'll just give the initials. So rather than giving you a boring introduction to the whole program or something, I'll just want to essentially have one example where you can see, where I think one can see especially well how things are working. And that's a good old quartic K3. So to start with gluing of 4 triangles, standard simplices, and that's what we always call B, and comes with a polyhedral decomposition. And then we have to specify charts for the integral affine structure. And they just look standard. Yeah, it's a standard thing for P2. So being specific, I really want the unit triangles here, 0, 1. So that would be a chart here. And then if we go to a chart here, well, it looks the same. But now this triangle that we had before, let's say we want to understand the affine structure along this edge, it has to come up here. So it would look like this. So that would be a chart in this neighborhood. And the difference of these two pictures tell you that you get some monodromy along the edge. And the monodromy, if you do the computation, it will look like 1, 4, 0, 1. You know, especially you see this is a 4 here, accounting to the fact that you could actually refine this affine structure by splitting this 1 point into 4 points. You know? So I'll do this later on, but maybe not now. I mean, what is the picture in general? I should maybe give you some idea of what's going on in general, because this may be a little too easy. In general, you would have a monodromy. So what is a monodromy? You would get, don't get too scared with all the notation in our papers. By and large, it's just this thing here. You would have an edge. What was my color? Orange, whatever thing. It's an edge, omega, and it sits in some codimension 1 thing, rho, that you should think of. Oh, maybe I should have drawn here. I indicate these points here where I cannot define the affine structure by some dots. It's a codimension 2 subcomplex. I mean, of the barycentric subdivision. So here you should think of this being somehow subdivided like this in dimension 3. And then monodromy, the rho, this codimension 1 phase, always separates 2 maximal cells. So you can start here at this vertex, go into the one maximal cell, go back, and then do the same thing on the other side. Okay? And the monodromy always has a very simple form. It fixes the tangent vectors in the hyperplane, and then it adds a factor, so it looks like p rho check. So that's the generator of the perp space. Lambda are the integral tangent vectors, yeah. And each cell comes with some integral lattice of rank equal to the dimension of the lattice. So you evaluate that at this, and then you just stretch in the direction of omega. So this would be an integral generator of the edge. And then there's a factor here that's called a omega rho, and that would be just an integer, non-zero integer, maybe 0 integer. So it would be 0 if you can extend the affine structure. So essentially, it's just one number. Okay, the affine structure is just the monodromy just tells you one number for each pair of an edge in a codimension 1 cell. Okay, and then you can there's a particularly nice class of singularities where which are kind of indecomposable. So this one would not be of this class, of this type. We call them simple. So I'm not going to take give the formal definition here, but among other things, it tells you that these a omega rho can only be 0 or 1. And some other conditions having to do with building certain polytopes out of these things and asking them to be elementary polytopes, elementary simplices, so simplices that only have vertices as integral points. Okay, so here we would have a omega rho equals 4. Again, you start with one vertex, you go into the maximal cell separated by rho, you go back, and then on the other side. It's a loop around omega through the two cells adjacent to rho. So a omega rho would be 4 in our example up there. Okay, so then we have this reconstruction theorem that tells us that given such a thing and some other data that I do not want to swipe on the cover today. So these are functions on the edges for each codimension 1 face and vertex. So you should think of them living here in a way. You get one function. So that's a Laurent polynomial ring. Yeah. So that's C of z1 plus minus 1 to zn minus 1. And then we have certain integers for each, again, for each codimension 1 thing that will come up in the equations that I'm going to write down. And then there's some kind of twisting that we call gluing parameters, gluing data, that among other things contains maps from lambda sigma to C star. So they will be used to change the gluing, the identification of monomials along the edges. Okay, and then there's a construction, gives a toric degeneration under certain technical conditions that are always fulfilled, let's say in the simple case. And that's a canonical toric degeneration involving wall structures and so on. All not so important today. And it's a 1-parameter family. And the only thing I want you to know is, first, the central fiber consists of the toric varieties with momentum polytopes, the maximal cells of sigma, of P. Yeah, so in our case here, it would just be a union of 4 copies of P2 in the example. And then we have a local equation looks like this. So if you have a vertex and a row here, you have tangent vectors, let me call them uv for the corresponding toric monomials on the adjacent components. And then there's a equation of this form. Okay, so it's as simple as it gets. So whenever f rho v is non-zero, it's just normal crossings, but it has some kind of funny singularities at these points where f rho v becomes 0. So let's do an example here. So let's do this example where I take just s equal 1, and where I take all f rho v to be of the form 1 plus w to 4, if w is a toric coordinate on this edge. Yeah? So this corresponds torically to P1 that has a monomial, and I want to take this thing here. So and what I get in this case, this family X turns out to be the dwarf pencil. Or maybe I should have said here, X also comes with a distinguished basis of theta functions. I mean, a basis of, so it's a polarized family, and it comes with the basis of the spaces of sections of any power. So we write some theta m, and the parameterizing set is a 1 over k integral point of B. Okay? So in here, for this dwarf pencil, sorry, for this case, I have 4 distinguished theta functions. These are just the integral points, theta 0 to theta 4. And then you see that this situation is so symmetric that the only equation that stays fixed that these theta functions can fulfill is just the equation given by the dwarf pencil. So it looks like, without knowing explicitly, like in our coordinates, what these theta functions are, we know there's an embedding of the whole family into P3, which look like, well, there's a certain function that can be fixed by period computations, but then it's like theta 1 to, what let's call theta 0 to 4 plus theta 3 to 4 plus theta 0 to theta 3 equals 0. Yeah? And that function can be fixed by period integrals that I'm going to tell you in a few minutes. So in this case, we know it. In general, we don't. Yeah, that's a very specific situation where you can actually write down things completely. So what are these kind of strange data, f rho v and s rho and so on? And how do they actually, what's the meaning of these? So there's a theorem, goes back a long time, that these, if you look at this set of pairs f rho v and s, I mean, the kappa rho is something discrete. And you could actually make, so what's the meaning of the kappa rho? You see, it occurs as a power of t. So the kappa rho can actually more generally take values in some monoid, and then the whole thing lives over actually a toric variety, okay, or the completion of a toric variety. So that's something discrete. But the non-discrete data are these pairs. And, well, there's a certain notion of isomorphism of these things that would make these families isomorphic. And then it turns out that this set is canonically the same, canonically isomorphic, to an affine cohomology group. Well, I'm not going to tell you how this works. But in the example, in the example of case 3 surfaces, so where you have S2, and now I would like to actually split these singularities. Let's say 24 points. Then I would get, then this is always the same group. You know? So for S2, with simple singularities, they are always 24 equals 6 times 4. we know this group, and it's just a torus. So this thing is just a lattice of rank 20, and then correspondingly, this guy here is a 20-dimensional torus. Whoops, C star to 20. So the picture is well, yeah, so I'm lying still a little bit, because that's not quite true. But I'll show you what it is. So that's some parameter space. Let's call it just S. And so I'm a little bit off because the family comes with a polarization. Now it always comes with a polarizing line bundle by construction. And as you know, there are many K3 surfaces that are not projective. So where do they go here? And there's actually an obstruction to projectivity of these families that have to be fulfilled for our program to run. So there's an obstruction map that you can write down in affine geometry. That's something you can find in the theta functions paper from January last year. It goes from H1, iota star, lower star lambda. Oh, what is iota? Did I ever say what iota is? I think I didn't. So iota is the inclusion of the complement of these dots. Complement of the singular locus. So you push forward the dual, and this thing is a dual tangent sheaf. Okay, so this thing here has a map to H2 of B with values in C star. So in the case of a sphere, it's just C star. And this is essentially a cup product with a natural class on this affine manifold called CB, the radiance obstruction. So CB is the radiance obstruction.
Really a C star in this, or is it defined at the Z level?
It is defined at the Z level. So if you write this down universally, you take the Z thing and then you evaluate. So the radiance obstruction, so this lies in H1 of B iota lower star lambda. That's actually integral. And it's a class of the extension given by the sheaf of affine functions, integral affine functions on B. So whatever this is, it tells you essentially it is an obstruction to defining your charts in such a way that they are not affine but linear. Okay. So in any case, it's non-zero, and then you need your gluing data to be in the kernel of the thing. So what you get is actually a subtorus, a 19-dimensional subtorus. And for any point when your gluing data are here, or this kind of pair f rho v comma s or somewhere here, you get a distinguished one-parameter family. So that's essentially the picture. So and then let's come to real structures. The whole construction, can you still see here very well, or should I go to the, it's okay? So the whole construction plays also well with subrings. So if your gluing data and the f rho v are defined over some subring of the complex numbers, then the whole construction will live over the subring. You never introduce denominators or anything. Okay, it's a bit surprising maybe, but that's a fact we proved. And in particular, if everything is real, then it's then the whole family will have a real structure, and you can measure this. So the family has a real structure well, compatible with the standard real structures on the central fiber. C is irreducible component. So X is defined over R, different only if F is actually defined in the Jota lowest lambda check tensor R cross, which is a real subtorus of this guy. Yeah? So it's clear there are many such real structures. Yeah? So this is something I proved with Julia last year. So and then, coming closer to symplectic geometry, there's also a momentum map. From the central fiber, some kind of singular momentum map. Yeah? So maybe you shouldn't take this too literally, but it's a map from x0 to b that when restricted to any irreducible component gives a momentum map for x sigma. Now that's totally trivial if you're gluing data, the S is just 1. If it's trivial, I mean, you just take your favorite momentum map that you know, and they will be compatible, and that's it. But using the theta functions, so that's under projectivity assumption. So using the theta functions, you can just define this, and then you get a momentum map for some U1 to n invariant Kähler form on the irreducible component. Yeah? So that exists always. So it will be non-standard if S is not equal to 1. But we get this momentum map. And now we can use this momentum map to build 2 cycles on x0. That kind of transfers to the codimension 1 skeleton, and also before I do that, I should say something else. Okay, in x0 there's some locus that is a bit of a nuisance, and that's called the log singular locus. So that's the 0 locus of these functions f rho v. Yeah, so that sits actually in the double locus of the central fiber. So in dimension 2 in the example, it's just points. Yeah, and then of course you have a map mu, and in general you just get, that's a hypersurface. Yeah, you get an amoeba image of this log singular locus.
I'm sorry. So what do you mean by non-standard?
Well, non-standard, I mean, it is the momentum map for some U1 to n invariant Kähler form. It's not the one that you would get by writing down your polytope and.
So the image of this moment map is just.
It's the same thing. It's up to diffeomorphism. It's the same. Diffeomorphical is the same. It's still the.
Is it still convex? Or
Yeah. It's sigma. The image is sigma. You just
x0, the full.
Sorry, what?
Image of full mu on x0, not just irreducible component.
That's B. No.
That's
No. I'm saying that if you restrict mu to one irreducible component, I wrote it differently. Okay. That's one irreducible component corresponding to sigma. The image is sigma. Yeah? Okay. And then you patch. Okay, so in let's say for dimension 3, you would have 2-dimensional row.
You twist the toric one with some coefficients.
Sorry, what?
For the moment map, you just twist the one you find in photon with some coefficients at the monomials, or what do you do?
What is that? No, it involves the theta function. You have to replace the monomials by theta functions, that's all. Okay, but we don't know what the theta functions are in general. Okay, so with non-trivial gluing data. So anyway, so so for n equals 3, you will get a certain amoeba image. It will intersect all those components where the A omega rho is non-zero. So it may skip some components, but it could look like this, for example. could have some holes. For our example, well, for the Dwark pencil, we really get the same thing, yeah? So it's really just this thing here. It's the same thing. But for other gluing data, this may split up, yeah? So this amoeba image may become any 4 points. Just depends on the absolute values of the zeros of your defining functions. It's a function of degree 4. Yeah, over there I had 1 plus w to 4. You can add any coefficients in the middle, 1 plus 2w and so on. And then the zero locus will split into various indifferent absolute values, and that will do that. And the cool thing is, something that I noticed only last year, I have to admit, that even in these situations, the complement of the amoeba image does have a natural affine structure. That is kind of a refinement of the affine structure you know outside, I mean, near the vertices. So I would know what the affine structure is at these points here, for example. And that has to do with the fact that you correct the affine structure that you have here by the argument of your f rho v's. So the argument f rho v's, if you have some rho, sorry, it's not the rho, it's the corresponding, how do I write this? So maybe the torus, yeah. So that's a c star to n minus 1. So that's a home lambda rho c star. That goes to u1. Oh, intersected minus a. Okay, outside of outside z. Outside z, you have a map to u1 because you have no zeros. That means outside the amoeba image, you have some winding number of the thing, and it changes when you go in here. It's called the, if you look in these old papers on amoebas, that's called the order of the amoeba complement. So this has to do with the order function on amoeba complements. Okay, so I'm telling you.
If you draw, like, say, in the case with a steer, draw the picture of the locus where these f rows are defined. Each one kind of lives where.
Oh, it's on a C star.
On a C star.
Right? I mean, like this 1 plus w to 4. That's a w.
No,
Is it?
on the center, here you're doing this thing over here is taking place totally on the central fiber. Right?
Yeah, that is also totally on the central fiber. I'm not caring about. I'm not doing anything for t non-zero.
Yeah.
Okay.
But it's, I mean, you have some hypersurface on the central fiber. That's what you're calling f. Right?
The zero locus of f is the
Where's f on the central fiber? Where on the central fiber is f? Makes sense.
It's a hypersurface in codimension 1.
on the double locus on the
Purely
toric
on
right.
double locus.
Yes.
Oh.
On this one component, yeah, it has an index rho, and that tells you the component of the double locus.
The three-dimensional case.
There is right. Sorry, you're a bit far away. N equals 3. Yeah. Yeah, it's worrisome if your co-authors ask questions of this kind, and you think, oh gosh. If you're confused, everybody else must be horribly confused. So please ask. Please keep asking. Okay. Yeah, please ask. Yeah, if you get confused. Okay, so right. So now the reason I'm telling you that you have an affine structure on the complement of these these amoeba loci, that since in codimension 1, yeah, so should think of some codimension 1 thing, but that sits in the codimension 1 cells and locally can kind of disconnect your B. Well, it's still in B. Yeah? But on the complement, I can talk about tropical cycles. So what is a tropical cycle? So now I'll come to work I did with Helge. So on B minus A is a one cycle with values in lambda. Now I don't need to write iota lower star lambda. So it's just, you should picture it something like, could be like this. So here is some singular loci, let's say. And then you have a cycle that could look like this. Not straight at all. So if I say tropical cycle, you shouldn't have the expectation that something is piecewise straight. But it carries an integral tangent vector. Okay? And at the vertices, so these are psi e, they live in lambda sigma. And at the vertices, you have some balancing. So the sum of these things, well, there's also some orientation, of course, right? You have to orient the thing. But then you get a balancing condition. Okay, so this is what I denote H1 B minus A lambda, and we get these tropical cycles. Now, when I have a tropical cycle, away from the amoeba image, yeah?
Yeah, maybe it's not clear. A is the A is the bunch of points. I'm just saying that because it might not be clear to everyone.
Okay, yeah, thanks. Right, so A, red, pink, or whatever this is. Right. Still confused? Go on.
Now you're in 2 dimensions, right?
This is the 2-dimensional picture. Sorry, I'm not so good in drawing 3 dimensions. Yeah, so in 3 dimensions, yeah, what would it look like? So, right. Shall I try?
No.
So you have something like this, right? And then there's the amoeba image in here, and you might have a hole here, and then you could kind of pass through the thing, yeah?
No, it's cool that you can do this.
Okay, so and then so you construct tropical 2 cycles first on sorry, not tropical. You construct 2 cycles on the central fiber first. Okay, so this is essentially a toric thing. Yeah, so the irreducible components are toric. So you just need to understand how these things give toric cycles. Well, over each edge, you can look at psi e perp in this torus. So that's well, actually a union, maybe a finite union, depending on the on the divisibility of psi e of tori c star to n. Sorry, s. No. That's a u1. Right. So that's a u1 to n minus 1. Okay. And then you act by this subtorus here, this u1 to n on your toric variety, and take a lift, essentially the orbit of a section of your momentum map over your sigma, to get an S1 to n minus 1 bundle over the edges. Okay. Then of course you have to be a little careful of what's happening near the vertices. Over edges. And then at the vertices, you have from the balancing condition, you need to glue in certain 2 chains. You can do that to make it a cycle. So for example, in dimension 2, you would have, let's say, that's the unfolded torus. Could have something like this. These would be the 3 cycles, and then you have to fill in let's say the thing here. Okay, that's just fiber-wise. So there's a procedure to turn tropical cycles into 2 cycles on the central fiber. And once you have a 2 cycle, well, the 2 cycles of the central fiber are transverse to the n-1 strata. And given, let me call this beta 0, okay, and given beta 0, of course, assuming we have an analytic model, we get retraction maps from the fiber t non-zero to x0. So we can kind of pull back the beta by this retraction map. So the beta 0 gives a whole family beta t for t non-zero, which I should admit is only well defined up to adding fibers of the SYZ fibration of fibers of the momentum map. Yeah, so this is well defined up to z times f, and f is an SYZ fiber equals mu fiber. Okay, and then the
So what does the cycle look like as it crosses from one component to the next of the central fiber?
well, in some cases it's totally harmless because this is just you just take the
Then you really get a cycle, nothing bad.
it's a cycle, yeah. It's just compatible at this thing.
Okay.
You just do the whole reduce to n-1, and
Tangent or something, you might have
it can contract in S1, but it need not.
Yeah.
It will contract in S1 if this vector is tangent to your boundary. Okay, otherwise it doesn't do anything. Okay, and then the theorem is when is that? What's that? 2014, maybe. That's the you can look at the integral, period integral, the canonical end form. So we have a canonical end form on x. I haven't said this, but that's the case. And then there's a neat formula that tells you exactly how to compute this. So it depends on gluing data. And then what was this? That I called it. That is not the CB. That's it's called delta beta trop. Okay, so what is this? So S was the gluing data. Yeah, there was a cycle in H1 iota lower star lambda check tensor C star, and then you can pair this with H1 iota lower star. Well, let's say lambda. Yeah, B minus A. Let's do iota lower star lambda here. We're in the simple case. So that maps to just to C star. Yeah, so it's an element of C star. This whole thing is a constant. And then we have a monomial. Yeah, and the power of the monomial is given by looking at how beta trop wraps under monodromy around the T circle. So the delta gives the monodromy action. So that can actually be taken also in here, H upper 1 B iota lower star lambda check, and it would map beta T to beta T plus delta of beta T, beta trop, times the SYZ fiber. So that's the topological monodromy.
Is delta the same as the CB on the right?
No, it's dual, right? It's that was the radiance obstruction, that's the C1 of phi. Hmm?
Radiance obstruction of the lower two?
Hmm?
I lost track. Is it the radiance obstruction of the lower two now?
Yeah, yeah. So the delta has something to do with this collection of these kappa rows. These integers that tell you, that live on the edges and tell you how this power, oh, I erased the equation, yeah? We had the equation uv equals f rho times t to kappa rho, yeah? And it is, as you can imagine, the t to kappa rho tells you how many Dehn twists you do when you pass, when you go around the origin. Okay, so we can also compute period integrals, these kind of period integrals. And it has the remarkable application that we know that we can compute the Picard group. That's not really topology, but well, essentially it tells you the integral structure on the or tells you which classes are 1-1 classes of the, which classes in integral cohomology are 1-1 classes. So at least in dimension 2 you can check this by checking that the integral that it stays perp to omega. Yeah.
Questions about this. You said two chains a bunch of times, but it's really an N chain.
Oh, I'm sorry. Yeah, it's you're perfectly right. I'm sorry. Yes.
Is there you started with basically a one-dimensional thing in B. Is there an analogous construction where you start with some higher dimensional thing in B, or is that?
Yeah, that becomes messy. I mean,
okay.
Yeah.
It becomes messy only because you need the single locus then.
Right.
Unavoid
That's the only case that is so neat.
Oh, okay.
Because you can avoid this amoeba image. Yeah. That.
I have a context question. So we're sort of in canonical coordinates
Mm-hmm.
on the modular space, but on the other hand, you're telling me that the periods have a really simple form.
Only these periods. The integral. These are the periods that compute the canonical coordinates. The periods you want to know are the periods for the SYZ section, and they are not of this type. Yeah. This is a W2 in the Hodge
These questions
filtration.
are related because if
Yeah.
you do what James suggested, then you get what you're interested in.
Yeah, these are kind of other cycles. Okay, but in dimension 2, that's enough. It's only dimension 2. In dimension 3, Calabi-Yau threefold, we only see that we have canonical coordinates, but we couldn't do the kind of period computation that would give you the Gromov-Witten invariance of the mirror. Yeah, but let me say this. So an application is you can compute the pec of xt. So let's do this for the case 3. So there you can see that the h1 of b iota lower star lambda, well, for case 3 it's also good because we have only these finitely many points, and then we know exactly what's happening at these points. So we can safely work with this thing. And then it turns out that this is always isomorphic to a part of the case 3 lattice. And we know exactly what part. So why is that? So first you observe, and to some people in this room who worked in symplectic geometry at the end of the 1990s, it's very well known that the monodromy representation, so this cohomology group depends only on the on the monodromy representation that defines this local system lambda. Okay? And that is unique for a case 3 surface, for an S2 with 24 singular points. We know it exactly. They all look the same. So you can compute this group in one model. And Margaret Symington did this. So there's a nice paper of Margaret Symington from 2D to 4D, where she gave an explicit basis doing exactly this. So you can write down, actually, it's tropical cycles she is writing down. If you think about it, it's actually tropical cycles. So she has a very nice model glued from two pieces that are kind of rational elliptic surfaces with some affine parallel boundary circle. And then you can see how you get exactly these things. How do we get the, so that's not quite the case 3 lattice. We are off by one hyperbolic lattice. Well, the reason is we still have these other two classes, exactly the same one that Paul was mentioning, namely the kind of SYZ section and the fiber. Okay, and you add these two, and then you get the case 3 lattice. Yeah, so indeed H2 case 3Z. So this is a SYZ section.
Is it actually trivial that this group is toric?
No, you have to compute it.
Is that what she's doing?
Actually, no, this follows from this thing, yeah? So I have a map into the, we know this guy is torsion free, right?
It's a check too. How do we know it's a check?
It's a unimodular lattice. It's a map of, it's an isometry of unimodular lattices. Must be an isomorphism.
I mean,
This is a unimodular
it
lattice.
computes that this thing is an isomorphism.
You have a map here,
Free, right?
and you know it's an isometry of unimodular lattice that proves that it is an isomorphism. Okay? Okay, so yeah, so then we can compute, right? So this now shows that now look into this thing, yeah? Where is my period integral? Over here. So to make this stay 1, there better not be a non-zero constant here, constant not equal to 1. So that would be the case, let's say, for s equal 1. Then we don't need to worry about this thing. But then this still varies. So we need this to be 0 for all these tropical cycles. Okay? So what we get is the perp space of delta sitting in here will be integral classes that stay 1, 1 in the family. So the perp thing in here, in H1 iota lowest lambda, give integral 1, 1 classes. So, well, that's rank 20. So this means it's rank 19. And the whole family is one of these famous families of repeatedly being discovered, I guess, first by Nikulin, then Aspin-Voisin, and then by Dolgachev. So this is this gives one of these distinguished families. So it come naturally out of these things. So if you ever wondered what these canonical families are, for certain things, they are also distinguished algebraic geometrically. Okay, so then let's go to the. I didn't use that big blackboard. Why not? Neatest one I didn't use. So okay, so this gives you some information. These period integrals and the construction via topical 1 cycles to get certain n cycles give you certain control of the topology. But there's more. And in particular, we would like to understand the real locus. Let's call it like this, xt real in xt. And maybe also xt. Yeah, both of these we would like to understand. And that works by what are called Kato-Nakayama spaces or Betti realizations. I don't have the time to tell you how exactly this is defined, but what is important is that it only depends on what is called the log structure of x0, and that can be read off from this data f rho v and s. Okay? And that has a Kato-Nakayama space, which is, as a set, just a Hom of log spaces. So it's written down canonically. Just writing it down so you see it's canonical. So this is a polar log point. Has something to do with real blow-ups and polar coordinates. So it's just a point, and then there's a log structure that's a morphism from some monoid to the structure sheaf. Structure sheaf for a point is C, and that's just polar coordinates. So R e to I phi maps to R times e to I phi. Okay? So there's a canonical way to write this down. It has a topology. It's only a topological space, okay? But when you then, I mean, there's a morphism of a certain pointed space to a certain log space. You can forget a log structure, you get a point. So this thing always comes with a canonical map to x0. You know? And then we can continue to B by our mu. Now, why are we interested in Kato-Nakayama spaces? The central fact is proved essentially by Nakayama and Ogis. Well, not essentially. I mean, it combines the result, fundamental result of Nakayama and Ogis in 2010, plus the toric local models that are proved, established with Mark in our part 2. That's not the reconstruction paper, that's another paper in 2007. That tell you that the Kato-Nakayama space of the thing actually reproduces the topology of an analytic model of the family. So let's assume we have an analytic family, let's say over disk. We can restrict it to a small circle. And then we get a certain family here. Let's call it, I don't know, XS1 or something. OK? And what this says is that this is just homeomorphic as a bundle to the Kato-Nakayama space of x0. So what's the S1 here? Well, our family comes with a map to the base. And the base has a distinguished point, the origin. And there's similarly a Kato-Nakayama space. So that's the Kato-Nakayama space. I should call it U1 maybe, OK? Because this is the Kato-Nakayama space of the origin embedded in the parameter space that I think I denoted S before. Yeah, so the upshot of this is there's some distinguished way to go from gluing data into a topological model of our degeneration. And the task is describes the thing as a torus bundle, as a topological object. OK, and that's what I did. So let's see what's going on. Let's do a very simple example. Let's take for B a union of two intervals. So it's not one of these Calabi-Yau cases, purely toric. It means the central fiber is a union of two copies of P1. Yeah, so and that's the moment map. And then what does the Kato-Nakayama space do? Well, the Kato-Nakayama space is actually functorial. So I should say the following. In drawing pictures, I will often fix here a face. Yeah? So I take the fiber of the Kato-Nakayama space for a face. So let's call this maybe x0kn, and then I fix some phase theta. OK? And any of these, the Kato-Nakayama space living over a maximal cell will just be the over an irreducible component will just be the Kato-Nakayama space of this toric variety. And that's totally simple. It's just a momentum polytope cross S1 to n. So what you get here, so this thing is a Kato-Nakayama space of this sigma, sorry, that's a sigma, of the toric variety, the irreducible component corresponding to sigma. So it's an interval cross S1, and you glue two such things together. OK, so what the Kato-Nakayama space does, it restores this kind of shrinking thing here. OK, and of course, the theta will tell you how you twist these two things. Yeah? I mean, that doesn't do anything topological in the simple picture. You can untwist. But if you imagine, let's say, we have an elliptic curve, it will do something. OK, so then here's the theorem. Let's go to the central. So the point is, so of course, we will be able to describe this nicely only over the complement of the amoeba image.
Where's the Nakayama is supposed to be the generic fiber, right? Homomorphic.
Yeah, it is.
How do the ends get filled in? Or are they filled in already?
Oh, the ends. Yeah, that's a bit. Yeah, I'm lying, right? So that is a case. That's a Calabi-Yau case here. Otherwise, you need a real blow up of this kind of toric boundary, the boundary divisor. So that would be the Calabi-Yau case.
But it also naturally happens.
Yeah, that naturally happens. Yeah, but you could just contract these boundaries, and then you get the what you would expect. I mean, the thing that fits into the statement. Thanks. Yeah. Okay, so let me just give this, let me look at my notes a bit quicker. So here's the theorem. It's in the paper with Julia. So over the complement of the amoeba image, so in dimension 2 is just over the complement of finitely many points. This thing here is homeomorphic. So as a torus bundle with continuous transition functions, or maybe differentiable transition function, maybe, to Hom P U1, and that's a U1 to n plus 1 bundle for this P fitting in the following sequence. Iota lowest to lambda, maybe just lambda because we only work over b minus a. So that's an x1 that lies in x1 of iota lowest to lambda z, which is the same as h1 of iota lowest star lambda check. And that's exactly where this monodromy class delta lived. Yeah, so the monodromy, of course, has to do something with the topology. So if I fix theta, this kind of phase, I will just get the Hom iota lowest lambda U1, yeah? Theta equals constant. That will just give this Hom P, lambda U1. And then in general, you get this P factor in addition, okay? So of course, that's not canonical. There's something more canonical, but on a much smaller subset. So if I just take the points, the vertices, and the interiors of the maximal cells, yeah, that's still connected, but rather small. We have something canonical. So let's call this B prime. And then this is canonically the same as the following thing. Now gluing data will come in, yeah? P hat U1. And so how does this come? So this now has an extension of U1 direct sum Z. P hat. Iota lowest to lambda. So that's now given the first component is still delta. And then it takes the arguments for just the phase of the gluing data. Okay? So this sits in x1, iota lowest to lambda direct sum Z. Sorry, x1 iota lowest to sum Z, Z direct sum U1. Okay? So that's canonical.
Maybe you're sick of me. I was slightly confused. I was expecting this thing is sort of like the SYZ federation, but it seems to be like one dimension bigger.
Yeah, because you have the phase, right?
Oh, it breaks up.
Yeah, so it's a mapping cone of the monodromy transformation. Sorry, mapping cylinder. Yeah. Of the yeah.
It's like the whole family. Around
It's a whole family.
That's awesome.
Yeah, so it's very important in mirror symmetry, I think, to have the whole family rather than just one symplectic manifold. Okay, and then and in this canonical description, I can tell you what the topology of the real locus is. Okay, so this is a lot of thing. So if this S in H1, iota lowest star lambda check tensor R cross. then the x0 kn real locus sits inside the thing as Hom p check and then plus minus 1 to n. Okay. Right. So I think my time is up. Then there is, so for K3 surfaces, let me just give maybe this last thing that I don't have time to expand on really. You can ask me afterwards. So for the K3 surfaces, there's a dichotomy. So I have B is an S2 with 24 points. And then we have either this this S is the theta is 1. Sorry, not the theta is 1. The argument of S is 1. It's trivial as a class. And then we have two components. So the real locus splits into components, and it's a 4-to-1 cover. Sorry for theta equal constant. Theta equal 1 of B of S2, and that thing has degree 1. So it's a section. And otherwise it's connected. That case is especially nice because the sigma 1 that will have genus 10. And then if you look at the Betti numbers, that's a 22, which miraculously is the same as the H2 K3, the second Betti number of K3. And if you're interested, you can find some reasoning why it has anything to do with one another in terms of Leray spectral sequences of the projections in papers by Castagno, Bernard, and Matesi. So maybe the real locus will be more important also in other cases to understand topology.
So what you say is that R gas is not 1, then it's disconnected. When R gas equals 1, that's this vanilla case, right?
Yeah.
Then you don't have a section, or you?
You do. The sigma 0 is a section, and the other one is 3-to-1.
Oh, did you write just the opposite of what you meant when you said R gas not 1?
No, sorry, there was some dirt. I didn't.
There we go.
Sorry.
So
Okay.
the sigma 1 is some kind of like rank 3 bundle on the mirror.
Yeah, I guess.
Do you have any idea what it is?
No. Good point, yeah. So even for K3, you can still find
Yeah,
things you don't know.
Oh yeah, way to go.